Hi everyone, today I am going to introduce Electromigration Immortality Check considering Joule Heating Effect for multi-segment wires. My name is Amir. This work has done by me and Liang under supervision of Professor Tan. I am working in VLSI lab under supervision of Professor Tan as a PhD student in the Department of Electrical and Computer Engineering at the University of California, Riverside. I got my master's degree in Electrical and Computer Engineering from Southern Illinois University and my bachelor's degree in Electrical Engineering from Sharif University of Technology. First, we show that why this is an important work and the motivation of this work. Second, I review the related works and introduce contributions of this work. Third, I propose our new temperature-aware voltage-based EM immortality check method. In this method, we find analytic temperature solution along a general tree interconnect considering Joule heating effect. We also find analytic steady-state stress solution in the presence of temperature gradient impacts. Then we show our numerical results and some comparison with recently proposed state-of-the-art EM immortality check method. Finally, we summarize our presentation. Today's with development of VLSI circuits, long-term reliability of VLSI remains a serious concern. In early failure analysis of blue waters at petascale computing, we can see hardware failure is up to 56% and mean time between failure was 6 days. Due to decreasing device dimensions, long-term reliability effects such as negative bias temperature instability, hot carrier injection, and electromigration get worse. Electromigration still remains the top killer for VLSI interconnect failures, especially at the nanometer region in modern VLSI circuits. Electromigration can lead to circuit failure through metal line resistance change and over time may result in void or hillock, as you can see. Electromigration, which is also known as EM, is a physical phenomenon of the migration of metal atoms along the direction of the applied electrical field due to the momentum exchange between atoms and conducting electrons. Electromigration was well studied and modeled by Cohen equations. An immediate side effect of electromigration is thermomigration, or TM effects. Metal atoms will migrate from high temperature to low temperature. As a result, the temperature gradients due to Joule heating contribute to the atom migrations. Thermomigration effects are mainly ignored before and become more announced as technology advances as shown in these figures. With development of VLSI circuits, the current density increases and the size of interconnect decreases rapidly, which leads to serious reliability problems if we ignore thermomigration effects. Because as you can see here, the ratio of TM flux to EM flux is more than 1, which means that in modern VLSI circuits with high current density and nanometer scale, we have to consider thermomigration effects. Many research work has been proposed recently for physics-based electromigration analysis. Some electromigration analysis research efforts, such as modeling, simulation, and optimization, which proposed by Professor Tan, did consider transient thermal effects, but didn't consider the special temperature or thermal gradient impacts on the multi-segment wires. For electromigration immortality check, which can be viewed as a steady-state stress analysis, bleach products was a widely used method for industry, but it only works for a single wire segment. Recently, voltage-based electromigration immortality check for multi-segment interconnect wire was proposed by Zeus-san, but no special temperature impacts are considered in this work. Abbas-Nasab in Rain paper investigated special temperature impacts on electromigration. However, the temperature of each segment from Joule heating is computed separately, which leads to accuracy loss. Recently, work proposed by Liang Chen and Professor Tan introduced semi-analytic solutions for transient analysis electromigration failure process. However, no electromigration-aware immortality check was studied. We computed Joule heat-induced temperature for all the wire segments in an interconnect tree, not separately. Also, we propose analytic solution to obtain the terminal temperatures of all the wire segments in a tree. Then, we derive the analytic steady-state solution for stress distribution considering a special temperature gradient due to the Joule heating effect. Finally, we propose the new temperature-aware voltage-based EM immortality check method. As we understood the importance of considering temperature gradient in modern VLSI circuits, we are going to find temperature distribution along a general multi-segment wire. Heat conduction in VLSI circuits is described by this governing equation. For the heat source, we consider Joule heating and convective heat transfer at the wire boundary, which are expressed as this equation. Joule heating power density is described by this equation where I is current, R is the resistance, V is the volume of the heat source, J is the current density, and ρ is the resistivity. Convective heat is stated as this equation where H is the coefficient of heat transfer, L is the characteristic length, and TO is the ambient temperature. As I mentioned, heat conduction equation can be expressed as this equation, and we can reduce the dimension of this problem from 3D simulation to 1D problem as this equation. As you can see, this term is heat flow from copper interconnect into surrounding dielectric, and this J2 ρ is from Joule heating effect. After solving the differential equation in the previous slide, we find analytical temperature solution for a single wire as this equation. With these boundary conditions, the analytical temperature solution can be rewritten as this equation with these parameters. As we found analytical temperature solution in the previous slide, now we replace derivative of temperature solution into these boundary conditions. If we call temperature at nodes as beta, then we should solve this system of linear equations to find beta or temperature at nodes. We notice that at terminal nodes, the related elements of beta are known already, which are called beta D. And beta U denotes unknown element of beta. Then the unknown temperature at nodes can be calculated as this equation. Then we have temperature at all nodes, which are called beta. By using analytical temperature solution from previous slide with boundary conditions of the related beta, We can find temperature distribution for a general multi-segment interconnect. Now we have temperature distribution for a general multi-segment interconnect, so we are going to compute a steady state stress. For a steady state of a system under material migration, we have these equations, and by integration of this equation we have this one, and again by integration of this equation we can show that the result is same as this equation. If the temperature distribution is same as this equation and A and B is very smaller than C, we can compute a temperature log integral for Tx as this equation. From slide 11, we have these parameters. And by replacing the previous parameters A, capital A, B, and C to the previous equation, we have this equation, and as a result we have this equation finally. For general multi-segment wires, stress also need to satisfy the atom conservation. The integration of stress for all branches can be expressed by this equation. To satisfy the atom conservation, we have these equations, where sigma 0 is the initial stress distribution. As a result, analytic stress solution for a multi-segment wire considering Joule heating impacts is obtained by this equation. Based on Ohm's law, the voltage of two-node wire segment can be expressed as this equation, where Uij is the voltage between node I and J, and Ui and Uj are the potentials at node I and node J respectively, and S is the cross area of the interconnects. Then we have this equation. With considering G as the ground node, then Uig is Ui and Ujg is U. The stress at nodes I and J can be given by these equations. By replacing these stresses to formula we got in this slide, and we can replace sigma I and sigma j here, then the result is same as this equation. This is a temperature over voltage based EM immortality check considering Joule heating effects and initial stress. This is a steady state stress at node G. Now we found analytical solution for a steady state stress. Then we can define a new temperature over EM voltage considering Joule heating induced temperature distribution of all the wire segments as this equation. Therefore, from equation in the previous slide, this equation, and this definition, the steady state stress at node K can be calculated as this equation, where Tk is the temperature at node K. If we define critical EM voltage as this equation, for any node we can derive the same voltage-based EM immortality check as you can see. Then we define a new effective EM voltage for node K as this equation. Then the stress at node K can be computed. These are very important equations for temperature over voltage based EM immortality check. This figure shows temperature distribution for a straight line interconnect. Blue is our results and red is COMSOL result, and you can see our results also the same as COMSOL results. And in this figure you can see effective EM voltage for a straight line. Also in this figure you can see our result also the same as the COMSOL result and more accurate than recent proposed state-of-the-art method called RAIN. In these figures you can see temperature distribution along a multi-segment interconnect, and also in this case our result almost the same as COMSOL result. Also here we validated our result by making comparison with COMSOL. As you can see, our result is more accurate than recently proposed method called RAIN. Here also you can see the importance of impacts of initial stress on effective EM voltage and EM immortality check. And finally, we show that in some special cases, effective EM voltage of two different initial stresses can be same if only if the integration of two initial stresses are the same. In this work, we have proposed a new voltage-based EM immortality check method considering the Joule heating induced special temperature gradient effect for general multi-segment interconnects for the first time. We found a steady-state solution for the electromigration stress considering thermomigration effects on general multi-segment interconnects based on voltage. Numerical result showed that compared to the console, our proposed temperature-aware EM immortality check method is much more accurate than recently proposed state-of-the-art EM immortality method called RAIN. Thank you for your attention.